integration by the Taylor method. We have a robot described by some state equation given here, and the input u1 and u2 is known. So it's given by this analytical expression with trigonometric functions. And with this and some initial condition, I have to propose a second order integration chain to obtain numerically a solution of this differential equation. This is my system. I have my robot where I have x1, x2, and my robot is represented here. It is the center of the robot. x1, x2 is a coordinate of the center of the robot. x3 is the heading, and I can control the derivative. So u1 correspond to the derivative of the speed, so the acceleration, like this. So the speed corresponds here to x4, and I can also control the derivative of the heading, so some kind of angular acceleration corresponding to u2. Okay, so I will recall what is the Taylor method for the integration. My system has the form x dot equal f of x and u. And I have in my state space, which is in our situation of dimension 5, I have x here. And if I know u, which is the case here, I have some ID of x dot. And if I start at this point, I will obtain a trajectory. And if it is x0 here, I will have x dot 0, and here it will correspond to the solution x of t. So if I know my initial condition, I want to compute an approximation of this trajectory. So for this, I will assume that I have an approximation. So I assume that I know here an approximation. I will call it x hat I will put it maybe here x hat. It is an approximation of x of t. And with this, I will have to compute x hat at time t plus dt. So if I consider my true solution, x of t, I know that x at time t plus dt, where dt is infinitely small, is equal to x of t plus x dot of t dt plus x dot dot of t divided by 2 dt square plus something which is infinitely small with respect to dt square. So here it is a second order Taylor expansion. Now this one, due to this relation, is equal to f of x of t u of t, and this one. So for this I will differentiate this one, and I will obtain that x dot dot is equal to partial derivative at xu multiplied by x dot plus partial derivative of f with respect to u at x and u multiplied by u dot. So I can replace this quantity here. As a result, the second order integration chain using the Taylor method is given by x hat at time t plus dt is equal to x hat of t plus dt, this dt, multiplied by f of x hat of t u of t plus dt square, this dt square, divided by 2, multiplied by partial derivative of x at x hat of t u of t times x dot, but x dot I know it is f of x hat of t u of t plus partial derivative, so this one, of f with respect to u at x hat of t u of t multiplied by u dot of t. So from this integration chain, I know that if I have an approximation of x hat, I am able to compute the approximation x hat of time t plus dt. For this, I need to know this one, f of x hat at time t, but I also need to know u of t and the derivative of u of t. So for this, I need to have an analytical expression for u. In my situation, here it corresponds to f of x and u. I need to have the second derivative to use in my Taylor extension. So for this, I have to compute the second derivative, x dot dot 1, x dot dot 2, and so on. So x dot dot 1, it is equal to x dot 4, so the derivative cos x3 plus so minus, because the derivative of cos is minus sign, so x4 x dot 3 sine of x3. Here I will have x dot 4 sine of x3 plus x4 x dot 3 cos of x3. I need also the second derivative for x3, and it is equal to x dot 5 x dot dot 4 is equal to u dot 1 and x dot dot 5 is equal to u dot 2. Now this one I can express with respect to the state using this relation. So x dot 4 is equal to u1. This one, x dot 3 is equal to x5. This one also to u1. This one also to x5. X dot 5 is here equal to u2. And I cannot replace u dot 1, u dot 2, except that from here I know that u dot of t is equal to minus sine of t cos of t. So I can replace this one by minus sine of t, and this one by cos of t. Again, u1, which is here, can be replaced by cos of t, and u2 here can be replaced by sine of t. As a consequence, I was able to have the second derivative of t as a function which depend on the state itself, u and u dot. So since I know the values for u and u dot, and depend on t. So it is this relation here that I can use in my Taylor expansion. As a consequence, the Taylor expansion that was given here rewrite as this. I have here x hat at time t plus dt, this one. Here x hat of t, here f of x hat of t, which depends also of t, because this one is known to be equal to cos of t, and this one to sine of t. This one corresponds to this quantity. Again, it depends of x hat of t and also of t, because all these quantity here, here, and here, they are known, since u1 dot is equal to minus sine of t, this one to cos of t, and u2 to sine of t. Okay. As a consequence, in the state space, if I know x hat of t, which is an approximation of the true x of t, I will be able to approximate here x hat at time t plus dt. I can reiterate the same integration chain like this, x hat at time t plus 2 dt, and so on. And the error between x times 2 dt when I will perform the integration algorithm, this error is of order 2, which is much more accurate than the classical Euler method, which is also a Taylor method of order 1. For the second question, I have to simulate the car for a time between 0 and 12 seconds with different integration chain: Euler, classical, Runge Kutta of order 2, and the Taylor method we had just developed in the previous question. Of course, u is imposed to be equal to this. The initial state is given by x0 like this, which tells us that the car or the robot is at 0 for starting, like this. There is a speed of 5, like this, and a rotation in this direction of minus half radian per second. The sampling time that will be taken for the simulation is not too small to see some differences between the different integration chains. I will first start with a simulation with an Euler integration. I propose the following Python program. Here it is the Euler integration chain, which is represented here. So I return the state plus dt times f of x and t. for the function f, it is given here, it depends on t, and the dependency with respect to u is given here, where I take u given by this function, which returns me an array cos and sine as given here, and I will extract the two components into u1 and u2, and then I will return as the last component of f as here. Now this, and this correspond to that in the evolution function. So this corresponds to f of x and u. Since u depends on t, I call it like this. I initialize the figure, I initialize the state, the sampling time, and I start the simulation. So 3m, like 3 methods. I will use this one to compare the 3 methods. So I have an integration loop where the state for Euler initialized to x0, sent as a parameter to this function, and k0 is just a function not to draw at each step, but every k0, where k0 is here equal to 10. So every 10 sampling time, I will draw the robot. If I start the program, I will get this. Okay, this is the integration corresponding to my problem. Okay. Now I have no idea how the Euler method is accurate or not. So that we do usually, we make some comparison like this. Instead of I will divide by t to have something smaller like this, and normally I should get the same trajectory, normally, if the integration is accurate. So I run the program, up, so all superpose. That's why here I will put smaller, like this, for instance. I run it, and I see that there is some differences, and probably when the dt is smaller, I am more accurate. So this is why I see some differences which tell me that the Euler integration scheme is not accurate. The Runge Kutta integration scheme is given here, and is implemented here, RK like Runge Kutta. So we use a function here, but also here at a different time. So the idea is when x at time t is here, this is f of x and t. Then the idea is to have a better following of the trajectory. We guess where will it be later with an Euler method. We check how is the vector field like this, and we make an average of the two, so that will be more accurate. And the order of convergence of the error is larger, so it means that I am more accurate. So this is the Runge Kutta, and I compare the Euler like this with the Runge Kutta method, and I will draw the robot red for the Euler, and for the Runge Kutta I will paint it green, Runge Kutta. It is also the same sampling time. Both Euler and Runge Kutta use the function f, which is the same as made previously. I run it, and I can see here that there is, at the beginning it is almost the same, but after there is some differences. But the shift after a while, when it comes back, the shift between the two methods almost disappear. So which one is the best? A good solution is for this, since we do not know which one corresponds to the reality, is to make again the simulation with a smaller dt. Okay, and I will put smaller car, so this corresponds to the size. The size is S here, size, and when I draw the tank, I put S as a parameter, so it will be smaller, 10 times smaller. I run the program, and I can see some kind of trajectory, and we see that the green is better than the red. It means that the Runge Kutta method is more accurate than the Euler method. With a small dt, we can see that there is a superposition between the Euler and the Runge Kutta. This is the Taylor integration scheme of order 2. To implement this, I need the derivative of u here, because I need here u.1 and u.2. I also need to program this expression, which was not the case for the Runge Kutta, and this is also why we prefer in general Runge Kutta. It is the main reason. But now with symbolic calculation, we can perform, we can compute automatically the derivative, which makes sometimes the Taylor method quite interesting. So here I compute this function here is computed here. So the second derivative ddx1 corresponds to this part. Okay. And this corresponds to the Taylor approximation of order 2. We recognize here the ddx corresponding to x dot dot, which is computed here. So the first component is ddx1, ddx2, but also u2, du1, so u2, du1 and du2 as explained here. Okay, this is a classical function f of x and t. This is why I can recognize here that it corresponds to x dot, which is denoted by ddx here. Okay, for the simulation of the three methods, I will call the Euler, the Runge Kutta, and the Taylor method, and I will draw with different colors: red, green, blue. Blue corresponds to the Taylor. So I run the program. I can see that the green and the blue superposes. It means that the Runge Kutta and the Taylor method are almost equivalent. We can see some green on this picture, but we can say here that they superpose, which was not the case between the Euler and the two other shapes. Which one is a true one? Again, I can do something like this. I divide dt by 10, and here I put the car smaller. I run it, and I can see that the blue and green, we do not see the green, but the blue and green correspond. So if I take dt very, very small, I obtain a trajectory here in blue, which can correspond to the reality, to the truth. For some application, we prefer to use the Runge Kutta method of order 3, 4 or larger. In the same for the the Taylor method, we can sometimes go to order greater than 10, for instance, if we want to be very accurate. Not in robotics, but when we want to predict the trajectory of planets, for instance.